Hi everyone, my name is Sofiane Abbar. I'm extremely happy to be virtually with you today to talk about our paper on spatio-temporal adjustment of traffic-oblivious travel time estimation. This work is done with my colleagues Rade, Stanojevic, and Mohamed Mokbel at Qatar Computing Research Institute in Doha. Travel time estimation is something that everybody is familiar with at this point. So this is the operation that allows us to figure out the time it takes to move from location A to location B, maybe at a particular departure time T. This basic yet important service is widely used by taxi and ride-hailing companies for different services of theirs, like routing to find the shortest or the fastest path between 2 points, fare estimation that allows them to figure out how much the customer will end up paying before the ride takes place, and finally, taxi dispatching that allows actually these companies to figure out which car, which driver to assign to a particular customer. Now, there are a few companies out there that provide travel time estimation as a service, usually in the format of APIs. The most important ones are Google Maps, here, TomTom, and Mapbox. And then in terms of customers, you could think of any company that works in the transportation domain. Here are some examples like Uber, Lyft, Muwasalat in Qatar, or food delivery companies like Delivery Hero. Money-wise, this is actually a big financial aspect for the companies. Like Google Maps, for instance, charges $10 per 1,000 ETA queries, or estimated time of arrival. And then a company like Didi would make around 2 billion of these queries per day. So this, as you could imagine, translates to a huge amount of money for these companies. And this is actually the exact main motivation of our work. Here at QCRI, we are very lucky to be working and collaborating with the local taxi company. And they wanted us to look at their data and see if we could help them reduce their bill on Google Maps services like travel time estimation. And this should be subject, of course, to things like comparable accuracy in terms of predictions, then response time and availability for their operations. As you could guess, we are not the first ones who have tackled this problem. Actually, travel time estimation is a long-lasting problem in the research community. Different approaches have been devised, and that can be grouped into 3 big families. So we have segment-based techniques, path-based techniques, and origin-destination-based techniques that I would describe very quickly in the following. So first, segment-based techniques. I mean, here we have a directed graph that represents the road network, and then we have some traffic data that has information of the pickup location, the drop-off location, then the actual duration of the trip, and maybe the time at which the trip took place. And the idea is to use this data in order to learn the weight of the directed graph. So the weights of every edge in the directed graph. Once you do that, the travel time to go from A to G, for instance, is nothing but the sum of the weight of all the edges that are on that path, in this case, 13 minutes. This is the most commonly used technique out there, and most of the commercial systems use segment-based approach. Now, one aspect that needs to be taken into account in this kind of techniques is the time dependency. As you know, driving for the same route in the morning of Monday is kind of different from driving the same route on Sunday afternoon, right? So depending on the departure time, you might experience traffic differently. And what people do usually is to split the traffic data based on some sort of time intervals, and then try to learn different graph models or graph weights for different time intervals. The problem with this technique is that in production, you will have to maintain different instances of your same graph. Now, in some other research work, people would try to learn the histogram associated with each edge. So this is nothing but a function that takes as input some sort of time and would return the appropriate weight for that time. However, this technique is never used in practice because we don't know how to optimize graphs based on time series or on functions. The second big family of work is driven by Christian Jensen and his team at Aalborg University. So the basic idea actually is to try to mine the trajectory data in order to learn the weight or the travel time of subpaths rather than learning the weight of individual segments. And this is how you could end up actually learning directly that the time it takes to go from A to G is 12 minutes. Most recently, people have looked into origin destination travel time estimation. In this case, they often actually completely ignore the structure of the road network, and rather they would split or partition the space into areas or zones like area 1, area 2, area 3, using different schemes, and then they would apply some trajectory mining or machine learning techniques in order to learn the travel time between pairs of locations at different times of the day, potentially. In our case, we wanted actually to mix the two most prominent techniques, like segment-based, which is widely used in the industry, and then this OD, origin destination techniques, to try to take into account the spatial distribution of traffic in a city. Now, our intuition is very simple. Let's say that we know that going from A to B takes for 10 minutes if there's no traffic. This is something that free flow routing engine could give you very easily. Now, if from my data or from my observation, I know that the guy is departing at 6 p.m. on Thursday, which is quite congested in the city. And then we know that the starting location A is in the Pearl, and then the destination B is in Al Sadd area, which is also known to be congested. Then it should be relatively easy to figure out that we need some sort of an adjustment to this for 10 minutes to make it actually 20 minutes. Simple. So for our intuition to be tested and implemented, we need three things. First, we need the map, which is like a representation of the road network that we would actually formalize as a directed graph. For this, we use OpenStreetMap, which is a fantastic open source project that I would highly advise anyone who didn't use it before to check it out. Second, we need the routing engine. So once you build your directed graph, you need to have an algorithm or a system that would find in efficient way the shortest path between any 2 points or nodes in the road in the graph. So you could try to implement your own solutions based on BFS with priority queues or Dijkstra. However, if you want to be really scalable for the level of country, you would have to implement more complicated techniques like contraction hierarchies. This is why we just decided to use one of the most prominent open source routing engines out there called OSRM, which is very efficient that many commercial solutions and systems use, and which provides actually very good paths between different locations. However, the travel time that it spits is, as you could imagine, is the time or the travel time in free flow scenarios, like the travel time when there's absolutely no traffic whatsoever. Finally, we need traffic data, and for this we are extremely lucky to get access to the data generated by the local taxi company. Now, the first thing that we wanted to check, right, is the impact of the temporal aspect on travel times that are generated by a system like OSRM. So for this, we plotted actually in the blue the hourly travel time, average travel time of trips that start at different hours of the day using OSRM. And as you could see, this is actually quite stable. So all the travel times are between 20 and 22 minutes throughout the day, which is of course like expected, knowing that OSRM doesn't know anything about the traffic patterns in the city. However, when we plotted the actual travel time reported by the taxi vehicles, we see that, you know, the traffic dynamics are there and they have this kind of impact. So we have this commute in the morning, and then we have the evening commute where, you know, where travel times are longer than usual. And even throughout the day, you know, the traffic actually is having some impact on the free flow travel times. However, for trips that happen, that occur between, you know, between midnight, or I would say even between like, you know, 11 p.m. and 4 a.m. in the morning, there's no huge difference. So these trips are not quite impacted by the traffic. And this is what we wanted to show, that depending on the hour of your departure, you might be experiencing like traffic patterns in different ways. Now, the ultimate objective is to figure out a way to make this blue curve match the red curve. The second dimension that we wanted to explore is the impact of the spatial distribution of traffic patterns. So here what we did is that we partitioned the city into its administrative boundaries or administrative zones. Like in Qatar, there are 92. And then for each zone, we would take all the trips that started from that zone, and we will look at their actual travel time. And then we would compare that travel time with the travel time generated by a free flow engine like OSRM. And what we could see is that depending on the region or the zone from which you originate your trip, you might experience delays and traffic in different ways. And this observation actually holds in other cities like New York City and Portugal and Porto in Portugal. Now, hopefully, I did convince you that both time and space have an impact that's not evenly distributed on the free flow travel time. Now, our problem of adjustment, of spatial-temporal adjustment, can be modeled as a supervised learning problem, where we actually try to learn an actual function of the real travel time for any given trip request that has a source, destination, and departing time. And for this, we would approximate this function with the machine learning model F that has a set of features. So these features include some free flow features that we extract from the routing engine that we are using, OSRM in our case. So we have the free flow travel time and then the distance or the length of the path that OSRM would return. And then we have some temporal features as well, like hour of the day, day of the week, hour of the week. And finally, we have some spatial features like the zone from which you are departing and the zone to which you are leading. Now, we also added actually some other features, like, you know, the total number or the ratio of trips that are originated from the source zone or destination zone, which captures actually the busyness of these zones. We have also some features related to the congestion at different times of the day that I would really invite you to read the paper to know more about these. But actually, once you formalize your model or your problem in this way, you could just apply any supervised machine learning algorithm for regression to figure out or to approximate the function of travel time. So in our case, we did trilinear regression, random forest, GBTs, and so on and so forth. And we tried to optimize also for the hyperparameters of each of these models. Now, in terms of architecture, so the most important advantage of our system is that it builds on any existing routing engine. So say you have your OSRM, which is traffic oblivious, it doesn't know anything about traffic, and then you get some traffic data from whatever company that's out there. What you could do is just to plug in your, our STAD machine learning module that would actually use the query parameters to learn, to extract some spatio-temporal features, and then it would query also the base routing engine to get this free flow kind of travel time that it would mix with the spatio-temporal features in order to generate the actual travel time. All our code and data is available on GitHub. I highly encourage you to check it out. Now for results, actually, I would focus on a few results for Doha, but in the paper, we also experimented with data from Porto and New York City in North America. The most important result is the following. Like in Doha, we report actually in this graph two things: the mean absolute error and the median absolute error, both estimated in terms of seconds. So blue is for mean and red is for median. Now this RE is the base routing engine, which doesn't know anything about the traffic. We have two versions of our system, STAD-T, which only accounts for the temporal features, and then STAD-ST, which accounts for both spatio-temporal features. And then we have our two baselines like KNN, which is an OD-based technique, and then Google, which is one of the most leading commercial solutions. So what we see is just by accounting for the temporal features, we could reduce the errors of the traffic oblivious system by 50%. So we go from a median error of almost 300 seconds to an error of like 142 seconds. And then if we account for the spatial distribution of traffic, we could reduce this further to 126 seconds, which is really, really, really good. So here we are like almost plus minus 2 minutes of our actual travel times. Now, the other interesting thing is that even when we only consider like the temporal aspects, we are beating and we are getting better results than the KNN technique and even Google Maps. The second thing that we did is to estimate the relative errors of our system throughout the day. So what we see here, like in the dashed curve, actually correspond to the errors, percentage error made by the basic routing engine, which doesn't know about traffic. And then the blue curves is the spatio-temporal STAD system, and we see that now the errors are kind of steady throughout the day, and they are below 20% in all cases. And I think the minimum was like 14%. We also looked at the impact of number of trips that we have or that we could use for training. And the common observation here is that for all the cities, the 3 cities, there was like sweet spot, like between 10,000 and 100,000 trips were kind of enough to get the best results in terms of accuracy. Finally, we also looked at the impact of the spatial partitioning, like the way you partition the city. Like we have two, so here we used 2 kind of zoning. We used the traditional kind of zones that we got from OpenStreetMap that are widely available for all cities around the world. And then we use like this, the red rectangle shows the actual transportation area zones that are designed by transportation engineers that work at Ministry of Transport and Communication in Qatar, and that they shared with us. And so what we could see is that it's true that using more crafted zoning scheme could lead to slightly better accuracy, but this accuracy, this gain is not dramatic, right? So just going with open source kind of zoning schemes is enough to get good results. Thank you very much. I think I'd stop here. And if you have any question, please feel free to email me at this email address. Thanks again.